All right. So, good morning, good afternoon, good evening, everyone, and welcome to day one of our live virtual training for SNET, WADA, Beyond the Code.ai, Meta language teaching, and hackathons. We are excited to have all of you here as we embark on this journey of learning, building, and exploring the power of Meta together. Today, we'll kickstart with introductions and our purpose for this program, then dive into understanding Meta from representing knowledge to integrating it into real world applications. By the end of the day, you'll be working hands on with a challenge that will set the stage for your project. Yeah, Nef. So I want you to take the lead, talk a bit about Beyond the Code.ai, and then I will talk about WADA and perhaps SNE.
Okay, great. Well, first of all, welcome everyone, and thank you so much for participating. I'm very excited to be here with the WADA team. I believe that the first organization I'd like to talk about are the developers in from Ethiopia that are a part of ICOG Labs. ICOG Labs is an AI research and software development company. It's a team of visionaries and software professionals dedicated to advancing the frontier in artificial intelligence research and application and delivering quality products to customers based in Addis Ababa and really all over the world. ICOG Labs was developed by GitNet and Dr. Ben Goertzel many years back before we had popular terms like vibe coding and AGI and BGI. So very proud to have the ICOG developers joining us in Kenya. They joined us in India for Hack India, and we're very proud to have them here. I'd also like to just say a little bit about Beyond the Code, and I'd also, if it's okay, can talk a little bit about a few of the other partners that are participating in this Kenyan-based real-world incentivized hackathon and virtual training session. SingularityNet is a decentralized platform for AI services founded by Dr. Ben Goertzel with the goal of creating open, interoperable frameworks for artificial general intelligence. It's home to MeTTa, reasoning language, the Hyperon cognitive architecture, and the AGIX token. SingularityNet pioneers research in symbolic AI, logic-based cognition, and decentralized governance to advance beneficial AGI. Another one of our partners is the newly formed ASI Alliance. The Artificial Superintelligence Alliance is a global collaboration between SingularityNet, Fetch.ai, Oceans Protocol, and Kudos. Together, they are building a decentralized infrastructural stack to support the next era of modular AI, combining symbolic reasoning, autonomous agents, privacy, preserving data, and distributed compute. A little bit about Beyond the Code. I'm one of the founders and the director and producer of Beyond the Code. We are partnered with SingularityNet, and Dr. Ben Goertzel is the executive producer. My business partner and founder of Basics is Saskia Natalie Betts. We have a host of other producers and partners that come along with us. Beyond the Code is an immersive AI documentary and development empowerment project. It isn't the typical Netflix docuseries. It's not a consumer-facing docuseries either. It's a strategic visual and cultural communicator tool inside the broader platform we are calling Basics. It was built to educate and inspire the ecosystem. We use short-form, authentic, behind-the-scenes content to show developers and real-world learners of AI, AGI, BGI, and all of the new technologies the world has to grapple with in teams and in terms of our wanting to make sure that the average Joe, the basic public, understands what developers are doing, who they are, and where the next products may come from. Basis is a strategic pathway to future-proof a developer ecosystem, and it's always on in innovation. So I want to thank WADA for partnering with Beyond the Code. It's been some time coming, and I want to thank ICOG, SingularityNet, ASI, and of course, again, the WADA team. They've been prolific in helping us put this together, and we're looking forward to the next few weeks in Kenya. And we hope that you all will join us and bring your best knowledge and open ears to learn MeTTa with Dr. Ben Gertzel. And also, we have Professor Malik coming in from Tubman University out of Harper, which is a Liberia based university. So, thank you so much, Sam. And I look forward to the rest of the program.
Yes, thank you very much, Nev, for that comprehensive information. I like to talk about WADA at a bit later when Yaps is done with the next session. So our participants can get hold of the detailed information we are giving as far as our partners or the stakeholders in this project is concerned. So, Yaps, if you can hear me, kindly unmute and take it over.
Okay, thank you, Sam. Let me share my screen and I'll give you a brief introduction about MeTTa and a small overview about what the problem statement would look like for the upcoming hackathon.
That works. Thanks very much, Yaps.
Okay. Okay, so everybody can see my screen, right?
Yes, I can see it.
Okay, cool. So before I start with the training, I would like to tell you a little bit about MeTTa and what kind of language it is. So basically, MeTTa is a sort of knowledge representation language with an added feature of reasoning and also programming. So the unique feature about MeTTa is it's like any other knowledge representation language you may know, like Neo4j or any other graph database. But in addition to that, you can also integrate logics and some programming logics basically into the query language. So it is the best of the two worlds, both the graph representation and the logic programming. So you may ask why this might be necessary, but I'll explain later, which is a very innovative idea. But before I go deep into that, I'd like to tell you a little bit about the problem statements. So we have around 6 problem statements that you're going to be working on after in the hackathon. It's going to be based on your choosing. Most of them center around the idea that we could use the meta language as a graph representation and the famous idea of using it as a RAG, which is a retrieval augmented generation. So you can do a lot of interesting stuff with MeTTa as a graph database or as a graph representation. So maybe my colleague will walk you through into the details of the problem statements, but I just like to tell you a little overview about what kind of things you should be expecting. We also have other problem statements that are going to be innovative with regards to the blockchain and integration to MeTTa. So just wanted to point that out. So back to MeTTa. So MeTTa is actually an abbreviation for Meta Type Talk language. So it's a language, as I told you before, that supports both logic and also graph representation or storing information. So it's actually a functional paradigm and a logic paradigm, which is a mix of the two. You might not know what these actually mean, but just to give you a brief overview, a functional paradigm is a programming paradigm where you use only functions. So it's a paradigm where where you use functions and variables that are not mutable in order to be able to run your programming logic. So unlike other programming languages like Python or C++, the functional paradigm doesn't actually have for loops or variable updates or those common things you used to know. Because it's a different paradigm, you need to be able to write functions and you need to use recursion and other things specific to the functional paradigm that you can use it to write programming logic. So the other thing is leveraging this, you'll be able to write logics depending on the data you stored in your graph representation. So we'll cover this in more practical terms later on, but I'll give you a little bit idea as to what this might look. So when we say logic programming, I mean there are different facts and different information that are going to be stored in your graph representation. And on top of that, you can write some, you can query those data, you can write some logics, and you can also use, you can also build on top of that in order to produce different kinds of logic. So that's what I want to mention. Okay, so the other part, as I've been mentioning so far, is the knowledge representation. So MeTTa allows you to represent any kinds of graph information in your database per se. I'll come to its more formal definition later. It's not actually called a database. So when you store a knowledge graph, like any other graph representation, you can use MeTTa, and on top of that, you can also represent hypergraph, which is actually a more advanced form of graph. So why MeTTa? So MeTTa has been developed as part of an open code project or SingularityNet project called Hyperon. So you may not need to know more about this because as it's not related to the hackathon, but the programming language is it has a unique features that allows the research that has been going on in the project named Hyperon. So yeah, the formal name for the database is actually called an atom space. So I'll come to its more definition later on. Yeah. So how does MeTTa works? So the first thing in MeTTa is you define everything as atoms. So this is the official terminology. Everything in MeTTa is an atom. So that's the simplest representation you can have. So an atom could be any symbol, or it could be any a graph or anything that you can put in your atom space or graph database. So that's the building block of any data you represent in MeTTa. So there is other types in MeTTa. The atom is the most generic type that you can get, but there are types called symbol, there are types called expression, and grounded atom. So this is all you need to know. I'll show you later on in the training session. So the other interesting thing in MeTTa is something called pattern matching. So as I mentioned earlier, you can access your graph information using querying language. So MeTTa's query language heavily relies on a pattern matching. So what I mean by a pattern matching is depending on the structure of your data in your graph, you'll be able to retrieve different kinds of facts depending on their data characteristics. And again, I'll come in detail about this during the training session. All right. So what other features MeTTa has is that it's possibility to be integrated with Python. So this allows you to extend MeTTa's functionalities into Python, which, as you can imagine, allows you to integrate it to a wide range of applications. So as I mentioned in the start of this presentation, I tried to mention that several parts of the problem statements are going to be related to RAG. So that will be possible because of MeTTa's integration with Python. As you can see, or as you have seen so far, LLMs have been very popular, and a lot of people use them or interact with them. And there are a lot of tools that have been developed with Python. So if you can leverage these packages or frameworks by also leveraging MeTTa's unique features, it's going to give you a very unique application. So the other is its ability to store hypergraph. I mentioned this earlier. Maybe I don't need to go detail into it, so I'll jump it. So yeah, the other thing is flexible representation. So when I mean by flexible, I mean that the way you store things in MeTTa is pretty easy once you get used to it. So different programming language, for example, let me just quickly mention this. Different programming languages have their code and their data separated. So what that means is that if you have some data that you want your code to access, you either need to call and to store it in a file, or to store it in a database, or to store it in an array or a variable, but you won't be able to treat your code as a data per se. So what that limits you to do is, once you write the code, you won't be able to modify it, or you won't be able to interact with your code. Only thing you can do is let it execute, and then use the data stored separately influence the way your code executes. But in MeTTa, both of them have similar representation, which enables you to do very cool things like rewriting your code in the middle of your logic, depending on some information, for example. So whenever a new information arises, you may say, okay, let me change this code. This code was not right, and you can rewrite it. And again, I'll show you more examples about this later on. The start of this presentation, you are able to write logic programs and also store information in your database. So using those information and using the rules you can write, you can write some inference systems that can use the data you stored and leverage your rules and also produce some form of conclusion and something like that. And the other popular use case is cognitive architecture or AGI experiments. This is something we've been doing in SNATE. As I mentioned in the previous slide, MeTTa enables you to rewrite your code. So once you define or once you write some code, you will be able to change it depending on a given algorithm or a given algorithm execution. So that allows you to leverage, or that opens a door to a several range of experiments that you can do with it. The other thing closely tied with the reasoning engines is an expert system. So this is slightly older version of AIs. I'm not sure if most of you have heard of it, but you can use MeTTa to implement this kind of expert systems. All right, so to set up with MeTTa, the only thing you need to do is to install a package named Hyperon. And once you do that, you can use the MeTTa command to run any .MeTTa file that you may have. All right, so going into deeper training about MeTTa, let me just mention these 4 types in MeTTa. So these are the 4 built-in types in MeTTa. So the first one is a symbol. A symbol is just anything that you can write, any Unicode characters that you can write that will be treated as a symbol. An expression is something wrapped within a bracket. So I'll give you an example later. Something that will be wrapped in a bracket, and it can contain within it different kinds of types. So it can have a symbol itself, it can have another expression, it can have the other types that I listed below. The other one is a grounded type. A grounded type is anything that comes from outside of the MeTTa interpreter. So this could be strings, it could be numbers, it could be Boolean values, it can even be functions that you defined in another language that you want to call from MeTTa. So these types are going to be collectively named grounded. The other one is variable. Variable is also a type. So in MeTTa, you can have variable, you can store variables in your database, then you can use them later on. So when I mean by variables, I mean variables in themselves without any content. So yeah, you can also treat them as their own separate type. All right, so what's an atom space? On the start of this presentation, I mentioned that the atom space is something like a graph database for other graph query language, for example. So in MeTTa, an atom space is basically the same thing as a graph database, but it's a collection of atoms. That's where it gets its name from. So an atom space is basically a collection of atoms. It's where everything you've written, everything you have defined, it could be logic, it could be facts, it could be rules, all of them are going to be stored in an atom space. And in MeTTa, you can have different types of atom space secluded from each other. You can have nested atom space, an atom space within an atom space, that is, and you can do all sorts of cool stuff with it. For the participants in the call, if you have any questions or would like to ask me, feel free to interrupt, and I'll proceed with my presentation. Okay, so let me just share my screen quickly, and we can go from there. All right, so I think everybody can see my screen. Okay, so yeah, in the previous slide, I mentioned there are 4 different types in MeTTa. So let me quickly go over those, and we can see how we can represent a graph information in MeTTa. So yeah, the first thing I mentioned earlier was a symbol. So a symbol could be anything that you write, a Unicode character. So this could be a symbol. You can also write some numbers together. You can just create any Unicode sequence. So for example, this could be a symbol. A name could be a symbol, and yeah, anything you write as a Unicode character is a symbol in MeTTa. So the other type I mentioned earlier was an expression. So an expression is anything that you wrap in between 2 brackets. So for example, this itself is an expression, which is an empty one. You can have something like this. You can write city. You can write different symbols. You can even drop in some numbers if you want. You can also write some other expression within it. So you can have another expression nested within a given expression. So yeah, this is what an expression is in MeTTa. It's pretty straightforward. The other type I mentioned earlier was a grounded type. So for starters, a grounded type is anything that has a different behavior than a symbol and is going to be treated differently with the interpreter. So one example is already something that I've written here. So numbers. Numbers are grounded in MeTTa, and strings are also grounded in MeTTa. So if you write a string, this is also going to be treated as grounded. Well, there are also some other functions in MeTTa which are built in. For example, this percent or a modulo operator or a multiplication operator or addition operator. Well, different functions. There are different grounded functions in MeTTa. So these functions are not an atom. Are not a symbol. They're not an expression. They're going to be named as grounded. So if you are interested, you can try checking the type of a function. Don't worry about the syntax for now, but we'll go over what everything else means. So yeah, so you can check the type of anything using the MeTTa's get type function. So let's get that out of the way, and I'll just come back to what all the syntax means over here. So yeah, these are the types in MeTTa, and you can have different types, and you can have different representations in MeTTa as well. So when I mean different representation, you can store graph-like data or graph-like information using MeTTa syntax. As I have already tried to store some over here, you can, for example, store an information about a city. So you can prefix that by saying a city. None of these symbols are built in just for your information. Everything you can change the name as whatever you like. I just named the city. Somebody can just name it C. If someone else prefers, it can say city, whatever you like. So I'll just stick with city. So you can put in the city's name within this expression, and you can also put in some other details like the area, which is 696 kilometers square. So when you wrap this information in a given bracket, so when it's in a single expression, that is, the MeTTa interpreter can understand that these are related to each other. So if you write it separately, it's going to stay separately. You have no way of relating these things together. So it's going to stay as a separate atom in our atom space. So if you wrap it in an expression, which is in a bracket, it's going to be treating it as a single entry of your graph information, for example. So for your graph, if you want to interpret it as a graph, this is where the part that MeTTa's flexible comes in. It all depends on the programmer. So if a programmer chooses to interpret this as a graph, that programmer can do that. Or if the programmer can just want to interpret this as a single node, it's also possible. The interpreter doesn't restrict you in that manner. So for example, here I'm just treating it as a node. So a given node named city, it has attributes near city name for a city name, Nairobi, and the city area, which is 696 square kilometer. So you can have different entries with similar structure. So yeah, let me just comment this out for later. Yeah, you can have different cities using similar structure. So keeping a similar structure will help you when you want to retrieve this information later. So I have some written already, so I'm just going to paste them down here. So we have different city information here, all with the same structure. So this same structure allows you an easy way of querying it later when you want to access different cities, different city areas, and so on. So the structure for now is they all have a prefix named city, which is their node name. And there is a city name. then there is a city area. So this is the structure I'm following. And again, this structure has been chosen by me. You can choose whatever structure you find useful for your own. So if somebody wants a different structure, or if somebody wants to add a different attribute, then they can do so freely, whatever they like. So yeah, this is how you can represent nodes. So then what? So in graphs you have edges as well. So you want to have some type of relationships, for example, between these nodes. So for example, in my case, if I wanted to use the relationship as the roads between different cities, then I can do so very clear. I can do so very easily using a different expression. So for example, I can write this expression using an edge named 2. So I can say from Nairobi to Nakuru. I'm not sure if I'm pronouncing it right, but never mind. So there is a road from Nairobi to Nakuru. So this is, again, it depends on how you want to represent your data. So I have a city named Nairobi, and the city's details are already presented over here, up there. So I can put that in the expression, and I can use my age. So my age depends on how I want to represent it. So this is where the flexibility comes again. So I can say there is road. I can use that as a name for my age. I can even put some weight if I want to. For example, if you remember, we can use expressions inside another expression. So I can say is road, or then I can put some number to indicate the kilometers. Or if I just want to put only the kilometer information, I can just do that. So and I will say from Nairobi to Nakuru, there is a distance of 123 kilometer, and there is a road. So it all depends on how the programmer wants to interpret the graph relationships. But the interpreter allows you to represent any kinds of graph relationships like so. So yeah, then let's just put in some more relationships between cities here. So using my first representation, I'm going to put a city name and at the ends of the graph, and I'm going to use an edge named 2 to represent that there is a road between the two. So yeah, just to recap, this means that there is a road between Nairobi and Nakuru. So there is a road from Nairobi to Nakuru, and the same goes for another road entry. So if I have different road entry from Nairobi to Kisumu, then I will just also input that here. And yeah, and for different cities, I just use the same representation. So you can represent your graph using something similar and very easy to write and to program like this. Okay, so what if I want to use a different representation? So a different representation means like if I want to store the ages, or if I want to weight the ages, for example, using the kilometer distance between different cities. So I mentioned a simple example before, and let me just paste more examples here. I can just say from Nairobi to Nakuru, there is a distance of 150 kilometer, but there is a road leading from Nairobi to Nakuru. And the same goes for all of the other cities. So imagine this is like a graph. So I already stored all the relationships a graph needs to have in a very flexible way using MeTTa syntax. So this information starting from right up here all the way to down here is a single graph information. There may be some redundant info here, but we'll come to that later on. But I'm trying to represent a single graph, which is the roads between different cities, and also the information about each specific cities. All right, so what's left? Then let me just quickly finish over some other examples. Let me give you some other examples about representing information in a graph, and yeah, we can go to the querying step. So in a graph, there may not be a hierarchy, It depends on your graph, of course, but there could be a direction. For example, here, I don't know how many of you are from a CS background, but if you learned your graph in your data structure, there is a directed graph and an undirected graph. So this one here is actually an a directed graph. Sorry. So it's a directed graph because MeTTa only knows that there is an entry there is a road from Nairobi to Nakuru. If you want to let the MeTTa interpreter know that there is another path from Nakuru to Nairobi, or that this path is undirected, then you have to do it on your own manually. So if I didn't define these entries manually, like, so if there is a road from Nairobi to Nakuru, then there is also a road from Nakuru to Nairobi, then the MeTTa interpreter won't be able to figure that out on its own. So you have to explicitly define the direction of the graph from which node to which node. Similarly, you can also do or store hierarchical information. So, for example, let's say you have another type of information in your graph. So let's say you want to store people's information. So if you have a person, then they may have a name, an age, and a major, for example. So let's say there's someone named Alice. Her age is 32, and well, let me make 62, and her major was computer science. So notice how I wrote computer science using a camel case. I don't have any space in here because if you put a space here, it's going to be treating it as two separate symbols. So if you don't have any space between them, it's going to be treating them as the same symbol. If someone prefers to use a space, then you may need to use a string so that it will treat it as a grounded string instead. So it's all depending on your preference. I prefer this format, so I'm going to write it as a computer science like so. So there is someone named Alice. Her age is 62. Her major is computer science. Let's also add her gender here. So she's a female. All right, so let's add someone else named Bob, who is 60 years old, and he is a male, and he is also a computer science student. So not a student, a computer science major, or he already have graduated. So you can store these kinds of people's information inside your database or your atom space like so. So what I want to come next is how you can store hierarchical information. So a hierarchical information with people could be their relationships to each other. For example, father-child relationship could be a hierarchical. So I can say there's someone named father. There's some father for someone. For example, the father's name. I can store the father's name and the child name. So, all right, let's just add someone named Charlie, and he's 19 years old. He's male, and he's a driver. So if we want to create a hierarchical relationship between, for example, Bob and Charlie, then we can define our own other entry, an expression that's going to be our entry for the graph. So we can say there's someone named Bob and there's someone named Charlie, and they have a relationship, a father-child relationship. So I'm telling the MeTTa interpreter or our graph, I'm storing an information in the graph saying that Bob is Charlie's father. So this is what this stands for. And again, remind you, this format doesn't have to be specific to the way I wrote it here. I can use whatever format I like. I can say, for example, Bob is father of Charlie. So if you remember, we can use any symbol as our relationship. It's just a matter of how we interpret our data later on. So I can even use this kind of relationship. I can treat Bob Charlie as their separate node, and his father is the same representation as the one above. It's just different. It's just a matter of how you interpret your data. So you can also, this is just to give you an example that you can also use MeTTa to store hierarchical information. And if, for example, Charlie later on has his own children, then you can say Charlie is the father of someone else. I don't know, maybe Jake. So Charlie is the father of Jake. All right. So again, another thing I want to point out, this information representation is very flexible. The interpreter won't enforce anything unless you try to query first. When you try to query, it will just look into the way you store the information. And again, it won't limit you there as well. I'll show you later on. It just depends on how you store the information and how you want to retrieve it. So it's all up to you. If you want to store the information like this, then you have to query the information like this. If it's like the above, then you have to do the same thing with the query too. And why I mentioned that is you don't necessarily need to have an entry for Jake to create a relationship between Charlie and Jake. So I have Charlie's information up here, if you can see, but I don't have Jake's entry anywhere. So the interpreter doesn't care as long as I don't try to query for Jake, which in that case it will just return empty because there is no one named Jake in our information. But you can create the hierarchical relationship nonetheless. And maybe if you want, you can create the information about Jake later on. The order really doesn't matter. The interpreter just will figure it out regardless of the order. So I can say Jake is a 3-year-old male student, and well, the major doesn't apply, so I'll just say none. All right, so you can use similar representation to store information about Jake. Okay, so I hope everything is clear so far. Just as a reminder, let me know if you have any questions, feel free to interrupt. Okay, so the next question is, well, once we're able to store information in our database or in our atom space, I'm going to be referring the database as an atom space from now on. So if we store some information in our atom space, how are we going to retrieve it? So to retrieve something from an atom space, we use a keyword called match. So this match keyword is trying to do pattern matching, the thing I mentioned earlier, trying to do a pattern matching and trying to retrieve the information from our atom space. So, well, a little syntax about MeTTa that I want to introduce is that this expression that I mentioned earlier, this whole representation we've been using so far, can also serve as a function call. So I told you that there is a function called match, which is going to be able to be doing a pattern matching, or it's going to query our atom space based on the query we gave it to retrieve its information. We can call that match function using the same representation, the expression. So when you put the function in an expression, if there is a function defined with this same name, which is match, in our case, there is a function defined. But if there is a function defined, it's going to call that function and give us its results. But if there is no function, it's going to be treating it as an expression. So it's pretty flexible. A function call can be treated as an expression, which can also be just a given entry in our database, as long as there is no definition for the function yet. But for example, if well, we can use the same example here. This expression and this match will have the same structure once we call it. Okay. Well, maybe let's just try to finish defining or calling this function first, and I'll get back to that in a moment. So what you need to know for now is this match is a function. It's a function that tries to retrieve information from our atom space. So it takes 3 parameters. The first one is, well, the atom space. So an atom space is usually defined using the ampersand symbol. It doesn't have to be, but usually we use the ampersand symbol. And for any code in MeTTa, we always have a default atom space called the self. So a self atom space is an atom space that is contained within the file itself. So this whole file that I've been writing on, starting from the beginning of this training session, can serve as an atom space, and it will by default be an atom space which is called as the self. So when you refer to as self or ampersand self, you're referring to the file that you're calling this match function in. So that's what this is for. So the first parameter is going to be the atom space. The second parameter is going to be your query. So can be your query can be like an expression. It could be a variable or it could be a symbol, depending on your information, how you store your information in your database. So something that I didn't mention earlier is that there is another type in MeTTa called the variable. So a variable in MeTTa is preceded with this dollar sign, and anything that has been preceded with a dollar sign is going to be treated as a variable. And you can use this variable in your query to represent parts of your information that you do not know but you want to retrieve. So let me just show you what I mean by that. Well, let's say we're building a query for cities. So if you remember, we have a city information stored like this. So let me just bring that over here. Yeah, so we have a city stored like so. So our data has this kind of format. So remember, our query should match the format of our data that we're trying to retrieve. So if we have a city stored in this information, we can say, well, I want the city, so I know that part, but I want the name of the city, I want the name of the city, and I also want the area of the city. So this is a valid query. So what I'm trying to say is give me all the cities, their name and their area. So when you define something as a variable, this variable is going to be replaced with anything that is going to be compatible with this pattern. So what I mean by that is, just to give you a little bit more explanation, we can put this query right alongside our information. So you can see the correlation between the variables and the information. So here, Nairobi corresponds with the city name in our query. The area corresponds with the city area here in our query. So this name is going to contain the name of the city that matches this pattern. So this is what I mean by pattern matching. We're trying to retrieve a given pattern from our atom space. So that's why we're writing it here. So this is a very flexible pattern. I'll come into it a bit later. But for now, let's just try to run it and see what the output is before I go into any further explanation. Okay. All right, so this is the second parameter of the match. The third parameter is going to be what you want to return once this match has successfully been executed. So in my case, I want just to return the name of the cities. And the only differentiation that you need to make between a function call and an expression, if you want to see the function call or the function executed, is to put this exclamation mark before the expression. So if you put this exclamation mark, the MeTTa interpreter will know that you're trying to treat this expression as a function call and print its output not into the atom space but into your console. So when you put this exclamation mark and run the file, you'll see we have a list of cities printed out here for us. So everything you see here was the city information that we defined earlier. So that's what the match is doing. All right. So once we got that out of the way, let's just quickly go back to how the pattern matching is working. So let's take this query and go to our data and see how things work. Okay, so think the interpreter as a big loop that's trying to iterate in your atom space until it finds everything that matches this pattern. So this pattern is telling the interpreter, saying that bring me any expression that starts with city, contains something here and another thing here. So those somethings and another things are represented by a variable. So the interpreter can fit anything in here that matches this pattern. So for example, if you look at this data, they all are triplets, and the pattern is also a triplet. So when it tries to match the triplet with the data is saying that, okay, what's the first part of this data? It's a city. Well, that matches the pattern. What's the second part of this data? I don't really care because the variable is, there is a variable here. It's not a specific value. So anything can match the second part. That gives us a lot of options because all of these lines match the second option because it's a variable defined here. And it also says what's the third part. It doesn't also care about the third part because we also made it a variable. So it's saying anything that has this pattern, the first has to be a city, the second one, it could be anything, the third one, it could also be anything. Bring me those things that match this pattern. So that's how the interpreter is working. To give you a contrast of how the interpreter is trying to run this query, if you have a different city, for example, here, the area, and let's say, I don't know, the place, the, okay, let's say we put the Kenya as a country here. So this city is in a Kenya, and we want it to be stored in our cities database. Okay, let me remove that one. So if you can see in our result here, we had the Lodwar as a city at the end of the results, but now we changed its structure. The query is expecting a triplet, but the Lodwar city has 4 entries inside the expression. So what happens if you run the query now? Well, the Lodwar will no longer be inside our executed expression. So let me just comment this out. Because as you can see, it's also retrieving the variable. It doesn't really care what the second argument is. Even if it's a variable, it's going to be printing it out. So yeah, as you can see here, there is no city Lodwar in our result. So that's because this data format doesn't match our query, which is a triplet. So it doesn't care what the values are, but it cares what the structure of the data is. So the first has to be a city, then the rest has to be just 2 values in an expression. So this is how the pattern matching is working. So you can make this query more strict by giving it more information about the pattern that it has to retrieve. For example, I can say I want to retrieve up the city Nairobi. I don't know the area, so I want you to give me what the area of that city is. So this will be returning only one value for us because we only have one entry in our atom space that matches this pattern, which is the city named Nairobi and its area. So we define the pattern, we constrained it by saying it starts with a city, and then there is the city name, which is Nairobi, but the area, you can put whatever area you want here. So let's just say we have 2 areas for Nairobi. Let's say one of the representation is just the whole thing as a meter square, but the other one is just storing an information as the kilometer square. So these are just 2 different representations for the same data, but they're both in our atom space. So if we do this, we're going to get 2 results because as you can see in our query, we don't really care what the last result is. We only care what the first 2 results are, and that the query and the structure of the data inside have to have the same structure or representation. That's why I told you earlier to keep consistent representations across the same nodes. So yeah, that's really that's pretty much it, what pattern matching is about. And again, the first thing, I made it a city, so it won't be matching any of our atom values in our atom space. So here you can see we also have other triplets and we also have other informations, but we're not matching that because our pattern always starts with a city. So the rest of the atoms in our atom space are going to be discarded as a value. Okay, so what if I want to retrieve the people I have in my database? So I can say I want you to retrieve every person. I don't care what their name is. I don't care what their age, what their gender, or what their major is. I just want you to retrieve everybody in my database. So previously, I was just returning one of the variables if the match was successfully executed. But now you can also return a whole expression inside match if you'd like. So you can say, well, I want you to return every pattern that matches this every data that matches this pattern. So when you try to execute this match, going to retrieve everyone who matched your pattern. So the first one is Alice, the second one is Bob, and the third one is Charlie. Oh, and we also have the fourth one, which is Jake. So yeah, it retrieves all of their information. One thing you need to note is that if you try to run this match before any of the data in our database has been inserted, for example, if you run this match before we input the name, the information about Jake, and if you try to run it, Jake won't appear in the results because the match is being executed before Jake and these other values were inserted in our atom space. So as long as you execute the match at the end, the order doesn't matter. It's always going to retrieve everything in the atom space. All right, so hope everything is clear so far. And yeah, that's pretty much it about the match. So let's dive deeper into what else you can do at this last part of the match. So first, at the beginning, we were just returning a single variable from our pattern matching, but now we're also returning a whole expression as a result of the pattern match. But you can also make another query nested in this return type. So you may say, okay, first I want you to retrieve, okay, let's change the query a little bit. First, you can say, I want you to retrieve who the father of Charlie is, for example. Remember this information here? We stored like Bob is the father of Charlie. So we can say, well, who is the father of Charlie? So the father will be a variable, since that's what we want to query inside our atom space. We can say, well, Charlie is someone's child, but we want to know who his father is. And then once we successfully queried the father's information, we can also return another match query. So we can call another match function inside this match function's return type. So we can say, try to match another information from the same space, which is the self space, and we change the query. We can say, I want you to retrieve every detail of the father. So this variable will be accessible. Any variable you put in your query will be accessible in your return type. So in our return type, there is a variable named father. So this father is going to be replaced with the actual value when we try to execute this match. For example, let's say the above query successfully run and it said it found Charlie's father, and it said, well, the father variable will have a value of Bob. So this will be replaced in our second match. When we execute our second match, the father variable will be replaced with the actual value Bob, and the rest of the query will continue. So that's what we wanted to do, because we don't know the father of Charlie yet, but we want to get all the details of the Charlie's father. So we can say, well, after you find the father of Charlie, you can make another query into our atom space, try to retrieve someone named Charlie, someone named, I've already started that here. Try to retrieve a person named Charlie's father, because that's his father's name is going to be stored in this variable, and we don't know his age. We also don't know actually we know his gender because his father, and we want his major or what his occupation is. Then we can say, well, most of the information are defined, but I want you to retrieve the father and the major. Maybe that's what we are interested in. Okay, so yeah, let's try to run this and see what it gives us. So yeah, as we expect, it's retrieving for us that there is a person named Bob who had a major of computer science. So we can do this nested match query and retrieve more than one information at the same time, or a nested query at the same time. So what else can we do here? We can also, this match function, we call the match function as a return type of match itself. We can also call any function here, any function you have defined, any function that is written in MeTTa or already grounded in MeTTa that you want to use. You will be able to use that, and I'll show you more examples about that later on. But here I want to introduce another type of query that you can use in MeTTa to to write more complex queries like the one above. So let's just write the query above just slightly in a different format. So as you can see, there is someone named father. Then we are writing a nested query, another query that is going to be dependent on the value of the first query. So we're going to do that again. And what we want to say is we are writing a composite query. A composite query is just a query that's going to be returning a successful result if all of the patterns we've specified inside this expression is correct or matches a result in our atom space. So let me just quickly walk you over as to what these are. So the first thing about a composite query is that it should start with a bigger bracket. So let me just rewrite it again. So it starts with a bigger bracket and you put a comma right at the beginning of the bracket. And once you put the comma here, you can put any number of queries following this comma. So we've put the father just like above, father of Charlie. This is our first query. Our second query was I want you to retrieve person named father, his age. I know his gender is male, and I also want his major. These are both of our queries that we put here. If you have a third query, you can also put your third query here. It doesn't really matter the size of the query. What matters is that this match query is going to be successful once we found a data set that's going to match all the queries we've put inside this bigger bracket with a comma. So yeah, the rest of the match structure is the same. It's just a little bit bloated. We can say, well, once you've run this query successfully, return for me the person's name and major. Remember, the father is just the name that we used in our query. We can just say this is father's name and change everything here accordingly, and it should work just fine. Just rename the variable names. Yeah. So these two queries, as you can see, returned an identical result, and yeah, we can have this. This will be easier to write more nested queries because, as you can imagine, calling match every time and nesting the structure will have a lot of redundancies like the space and the return type, and the match function call itself will become our code will be a bit bloated very quickly. Okay, so this is all about the match function that I want to tell you. But I also want to mention a little bit about what I meant previously in the slide presentation, that you can also manipulate the graph database using runtime function calls. But in addition to that, you can also rewrite your own code using MeTTa. So first, let's just see how we can manipulate this atom space at runtime or using functions. So once you defined different entries like so, you can use two functions. One function is a function called add atom. The other one is another function called remove atom. These are your space manipulation functions. So when you add an atom, let me just put match here to see the resemblance. When you add an atom, you have to specify the space again. So you can say, I want you to add an atom. And if you remember, an atom is anything in MeTTa. So it could be a symbol, it could be an expression, it could be grounded. Everything could be an atom in MeTTa. And when you want to add an atom, you specify the space first. So you say, I want you to add an atom into the space, the atom space self, which is the file itself. And let's say we want to add a city information about Addis Ababa, which is the city of Ethiopia, the capital city of Ethiopia. So let's say we have Addis Ababa and 106 square kilometer, which is its area. And we try to run that. All right, so what this does is it's going to add this atom inside our atom space. So our atom space is a self. So if you see up here, we didn't add the Addis Ababa entry up above here, but once we call the add atom function, it's going to be as if we've written this entry into our atom space. The only difference is that that expression or this entry is going to be added into our atom space at runtime when we try to call that function. So it was not here in our atom space initially, but after we call the function, it's going to be in our atom space. But the add atom function doesn't really return anything. That's why we see this empty expression as when we try to call it. So if we want to verify that this has been added into our atom space, we can use our self to query the space. We can give it a name, and we can give it the area. Or we can just say, I know the name is Addis Ababa, just make sure, bring me what the area of that city is. So if we run this, as you can see, we get the area of Addis Ababa. But if you run the same much before the add atom, you're going to get an empty result. This empty square brackets indicates that there has been no entries found in this atom space. Okay, so this add atom is able to add any expression or any information into your atom space. So that's all about it. Well, the other similar function is our remove atom function. Our remove atom function is the same as our add atom function, which you can use to remove a certain atom from your atom space. So you're going to give it the atom space, just like the add atom, and you're going to give it the data, the exact entry you want to delete from your atom space. So the main difference between this add atom and remove atom function and the match function is that the match function takes a pattern. It doesn't necessarily need to take an exact entry. Of course, you can use the exact entry. Of course, you can use the exact entry and the match function will execute successfully, but then you're not actually retrieving any new information. You're just trying to make sure whether that information exists in your space or not. For example, I can say if this is matched successfully, I can say true. So what I'm trying to do is if there is a function, if there is an entry named city Addis Ababa and its relevant area, then I'll just say true, Addis Ababa exists in my database. So as you can see, there is the result true here. So you can do that in using the match function. You can either use an exact entry or you can use a pattern. It depends on you. But when it comes to the remove atom and the add atom, you actually need to specify the exact entry that you want to delete. So if you fail to specify the exact entry, the function won't throw any error. It won't just remove the entry you wanted to remove. So yeah, when I say remove atom, Addis Ababa, I give it specifically every details it needs to know. So let's just run the match below it to make sure everything exists or has successfully executed. So let me just comment this out. And yeah, let's run this again. Oh yeah, I didn't add it, my bad. Okay, so after I've added it, you can see there this match successfully executes, which is why it's returning the area, as you can see here. But then after I remove the city from my atom space, then I can no longer find the city Addis Ababa in my atom space. So I can use this remove atom to remove atoms from my atom space. So this will become very useful when obviously to do or perform CRUD operations on your atom space, but it will also become useful for other use cases that I mentioned earlier, like for doing some interesting project that tries to rewrite its own code and stuff like that. So it's very useful and very unique feature in MeTTa. So one may ask what makes it unique, because I can also manipulate different graph representations in different languages. In MeTTa, I mentioned earlier, in MeTTa, a lot of functions, or almost all functions, unless they are grounded functions, are represented using the same structure, like the atoms here. I provided it here. So you can see I've been defining a person, Charlie, and different cities, different relationship the cities, all information's up there. So all of them are enclosed in a bracket. So even when you try to define a function, it's going to have similar representation. So, well, let me just show you a single function definition and you'll see what I mean. Okay, so when you try to define a function, obviously you start with an expression and you use this function called equals. So this is an equality operator. It's not an equality operator like the other functions, another programming language where you try to assign a variable, but this is actually assigning a function to its name. So when you say equals, you define the function name here. So the function name is going to be enclosed in another expression itself. The first entry is going to be the name of the function. Let's make it foo. The second one is going to be the parameters the function is expecting. So you can have x, the first parameter, y, the second parameter, z, the third parameter, and you can keep going as long as you want. You can even have a function with no parameters, and you can define, well, I just want a function named foo, and I want it to always say foo. I keep misspelling it, that's weird. So yeah, you can define a function like so. And you can call the function, as I mentioned earlier, when you want to call a function, you have to provide this exclamation mark and open a bracket, write the function name, and then the function parameter. So this is very different than how we call a function in any other programming language. Most of the programming language, you write the function name, and then you open a bracket, then you provide the attributes. But in MeTTa, it's the other way around. You first write the function name inside the bracket, and then you write the attributes. So it's actually pretty easy once you get used to it. So, well, our function named foo doesn't really have any parameters, so I can also change this to be a symbol instead of an expression, but it doesn't really matter. And let me just comment this out. Okay, so let's run this and see what we get. Yeah, so we get the expected result. Once the function foo is called, we're expecting it to return this expression. We can also do something similar by saying that when we call the function, we just want to return a symbol, and that's also possible. So just to recap, the function definition is itself included in an expression. The first argument has to be, the first element of this expression has to be the equality operator, which is actually telling the interpreter that this is actually a function. And then we can have this function name followed by the parameters. So let me just add some parameters here as an additional example. So we can have a function name followed by this parameter, and all the parameter you want to add should be included in this nested expression. Then after that's done, you can have a function call or the actual function return value that's as a third argument. So as you can see, a function definition is an expression with an expression of triplets. The first one is going to be the equality operator. The second one is going to be the function name along with all its arguments or parameters it's expecting. The last one is going to be the return value of the function. So yeah, as you can see, the other feature of MeTTa is in another different programming language, when you define a function and when you call the function without the appropriate arguments, or if you are trying to call a function that has not been defined, it's going to be throwing an error. But in MeTTa, it's going to be treating it as an expression, because as I told you, the function definition and any expression can be interchangeable with each other. So the MeTTa interpreter will try to find a function called foo, which doesn't expect any parameters, but it couldn't find any. So it's just reached to a conclusion that, well, there must be no function definition. So this is just an expression. So I'll just print it out as an expression. So it will be just the expression you printed out over here. But if I remove this x here, it's going to be executing it and return foo. Well, we can just change it into something else to return 1, for example, and we can see it's working just fine. So let's just change the definition a little bit and see how everything works. So if you put an argument here or a parameter here, you'll be able to access this parameter's variable throughout the function's return value. So the function return value doesn't really have to be a single value. It can be an expression. It could be another function call. It can be a very big expression. Let's say, for example, you called foo with x. So this is a valid return value in MeTTa. So yeah, as you can see, you called foo with x. Yeah. So this is how you define function in MeTTa. So what I want to direct your attention to is that those two functions I showed you earlier, the add atom and the remove atom functions, you can manipulate these functions like any other expressions. For example, if I haven't defined this function definition first, but I wanted after running a few lines of code, I can say, well, I want you to include in my atom space, which is the self, no, not much actually. I want you to add an atom into the atom space for this function definition. So I haven't defined the function. As you can see, I've commented it out. Well, I'm sure you have noticed by now, but we use a semicolon to comment it out. A single semicolon also works, but I prefer the double one. So I've commented out the function definition. So if I try to call the function like so, it won't be returning anything because there is no function definition named foo. But if I try to add it like so, it should work just fine because now I have added this function definition into my space. So you can imagine if after you've written a function, you can change its value by removing it from the atom, changing its definition and putting it back into the atom space, or you can just add a new function definition based on your execution logic into your atom space. So this is the part that I was mentioning again and again, that MeTTa allows you to rewrite your code. So just wanted to mention that. It would be awesome if you understood it, but it's okay, you just get used to it as you practice more. Okay, so we've seen what the function definition looks like. And well, the other thing that I need to mention is there are some built-in functions, as I tried to mention with match, for example. Those other functions is going to be, well, as I mentioned earlier, you have some small grounded functions like multiplication, you have a division, you have an addition. These are just the basic grounded functions that are built into MeTTa. So one thing weird that you will be noticing is that these functions are actually in prefix notation, not in an infix notation. For example, there could be some other programming language. For example, in Python, you can say, well, if you want to multiply two numbers, you'll say 2 times 3, then this will be stored on a variable named x, stuff like that. But in MeTTa, it's going to be in a prefix notation. So you rearrange this function call and you make it an expression, because as I told you earlier, a function call always starts with an expression, and it always starts with this exclamation mark. So you say it times and then you add to the rest of the argument toward the function. So every function in MeTTa follows this convention. Every function starts with a function name. In our case, it's a multiplication. Then it follows with its arguments, which are 2 and 3 for our case. So if you run this, it will be successfully executed and returned to us 6. So this goes to all of the other functions. So if you try to divide this, it should work. Well, the last one expects more than one argument, but we're not giving it any, so that's why it's throwing an error. And this is casting it by default into an integer, which is why it's 0. But if we change it to 1, then to 3, it will return to us 1. And the same goes for this one as well. Yeah, just wanted to mention that. So this is part of MeTTa's unique behavior. All functions are going to be represented in a prefix notation, and they're going to be enclosed in an expression. And actually, everything also in MeTTa, if you write a logic, that is, if you write a logic, everything that enables you to write that logic is going to be a function. So here we try to match from a space, which is using a match function. We add atom into a space using the add atom function. We remove atom space from the atom space using the remove atom function. So why I wanted to mention that is that you can write you can use different built-in functions in MeTTa, and it's all going to follow the same pattern. And I'll circle back around to this concept a little later on. But first, let me just go on and let's just define some more functions, some more useful functions instead of just a full function. Okay, so let's define a function. It's going to start with an expression again, and then we have this equals sign here, and then we write the function name. And this time, let's say we want to get the name of a given entry. We only wanted to retrieve the name of a given entry. So yeah, we give it this one, and well, maybe let's make it more useful, and let's say get age of for a single person. So we give it the person's name, and then let the function run. So, well, the function has three parts. The function definition. The first one is the equality sign, which is always the same. The second part is the function name and the parameter. The function's name is get age, then parameter is person's name. And the body is going to be, well, we have people information stored in our database, so let's just use this match function, retrieve from an atom from our atom space using the query person name, age, major, and I think that's pretty much it. Oh, I forgot gender here. Yeah, it has to match our data that we have stored. So let me just bring one of the data here so that we can use it as a reference. Okay, so yeah, we have this, and we want to retrieve the age of this person. So we matched from our atom space a person with this person name, which is going to be given when we execute the function, and we are going to return the age from it. So yeah, when we run this function, we will be giving it, when we call the function, we can give it the function any person's name, and it's going to be returning to us their age. Okay, I think there is something wrong. Let's try to figure out why. There a variable I've declared here? Yeah, this was the one causing a problem. So yeah, we retrieved from our atom space a person named Jake, and we found out what his age is. And we can write different functions like this. We can write get major and use this person's name as a unique identifier and retrieve the major of that person. And yeah, we can call the function get major of Jake, and it's going to be returning to us as none because Jake doesn't have any major. Okay, so these kind of function definitions are more useful, but I'm going to show you another feature that you can access in a function definition, which is a pattern matching. So part of the beauty of using similar representations for functions, matching, and your graph information stored in a database is that you have some features that are going to be able to apply to functions where you found in match. For what I mean by is that, for example, we have a pattern matching inside our match function, but we can also have similar pattern matching inside our function. The only difference is going to be the match is trying to pattern match this whole expression from our atom space called itself. So it's going to walk through step by step in our atom space and find everything that matches this pattern. But for it, when you put it in a function, the function is actually going to be matching a single variable, which is going to be passed to this function as an argument. So the same representation could be, I can say person here. So this and this one are similar. This one is just without any pattern matching. So if I am sure that this function always gets a person data as an argument, I can pattern match the person data and already pre-access some of its values like the person's name, the age, the gender, and the major using pattern matching. But if I'm not sure, or if I don't know the structure of the person, I can just say, well, I just want you to use this person as your information and then be done with it. But the get name function won't be any useful if I just give it without any pattern matching. So why I wanted to show you this one is you can also pattern match inside a function. And well, here we can access these variables and return the person's name. So if I say get name, I have to give it the data, remember? So let's say the name is Jake, or I make this, okay, actually it's fine. The name is Jake, the age is 3, his age is 3, gender is male, and major is none. So if I give this value to the getName function, it's going to return the Jake because it was successfully able to match the pattern between the called argument and the parameter of the function and return the variable from within the pattern matched argument that we defined above. Okay, so you can write some other functions that are quite similar like this. Let's say get I don't know, you can define, well, this brings me to another feature in MeTTa actually. That is, in different programming languages, if you define more than one function, that function is going to be treated as an error, or you have to make sure they have to be overload. So in MeTTa, you have some form of features that is quite similar to function overloading in another object-oriented programming or any different any other programming language which supports function overloading. So let's say we are defining another function with the same name, getName. And for this one, let's say we're actually not going to be getting a person, but we'll be getting a cat. So the cat will have a name and an age. So given that, we can say, well, the cat's name is going to be, well, the cat's name. So using the pattern matching, we can also define another function which is going to be an overload for a dog. So the dog also will have a name and an age, and will be returning the name of the dog. So depending on what kind of data we're going to pass it down, the function will be able to infer which data is supposed to be returning. So if I say cat, and let's say for the name of the cat, Luna, and the age of the cat is 4. And let's also call this a dog whose name is Max, and he is 3 years old. So if I run this function, the function all returns successfully and different. It has a different behavior. So you can imagine how you can use function overloading to create different function definitions with the same function name, which will supposedly have a different different behavior. So that's also possible in MeTTa. All right, so now let's write some other functions which are going to have some more logic into them. So instead of just pattern matching, let's just define another function. For example, let's just define a function named isEven. So it takes a variable, which is any number, and it makes sure it returns whether this thing is an even or an odd. So in MeTTa, you have this function called modulo. So in Python, this is also a common function. So it's going to be returning the result of the remainder of dividing the variable with 2. So if this is 0, then we're going to be returning true. If it is not 0, then it's not even. So it's going to be returning false. So there is another function in MeTTa called double equals to. So this function, well, just like any other programming language, is going to be comparing two values. So we are going to be comparing the result of the remainder of dividing x by 2 as to being 0. So if this is going to be 0, then, well, this is going to be returning true. If it's not 0, it's going to be returning false. So just to give you an idea of what this looks like, we can have a sample execution here. So for example, I can say, what's the value of this? And the interpreter will say it's true. So just to give you a more deeper understanding of what we're doing here, let's just log both of them. So the modulo of 4, when it's divided by 2, is going to be 0. If I change it to 5, it's going to be 1. So we're going to use this return value and nested here. So we can compare function's result, which is going to be returned when the function is done executing, with 0. So if this function returns 0, then this whole function's execution is going to be returning true. So that's what we're doing here. The function named isEven takes a variable x, and then it takes that variable x and returns to us whether that's even or odd. So let's try it out. Is even, it says true. If it's 5, it says false. So that's how we can define another function using some logic. So, well, we can also define another function called isOdd. And we can use the function isEven and negate its value to be the body for our isOdd function. So if it's not even, well, certainly it must be an odd number. So we're going to call the not function over the isEven function. So let's say is odd here. So let's see how it goes. So the first two are going to be true and false because 4 is even and 5 is odd. The second one is going to be false and true, which is the expected result because 4 is odd and 5 is even. So this is how you can define your own functions. So let's just cover one more thing, which is going to be if conditional in MeTTa. So most of the time when you write a function, you need a control
Hello, yes.
logic. Yeah. Yes.
Before we cover that theme, are we able to pause and maybe ask if anybody has questions or any contributions
sure.
at this point before we continue, so that you can have a sip of water or something, and then we'll come back to it.
Sure, we can do that. So, yeah, if anyone had a question,
participants on the call, at this point, if you have any contributions, any questions bothering your mind, I think it's a good time now to come through, and then we can move on with the other modules that Yaps was about to introduce to us. Shivaji, you have been on the call since we started. How is it going for you? Are you able to unmute and tell us something?
For me, it's fine. I do not have any questions. I think it's content. At present, I do not have any questions.
Yeah, thank you very much for that feedback. Thank you. Frida, you joined midway along the session. How are you feeling? I guess you missed part of the introduction, but how is it going for you? Okay, so Frida says in the chat he has no question. That's great. Abdulaziz Alasan, can you say hi to us? You just joined, and how is it feeling? How's it going for you? Abdul, are you able to unmute and tell us something? All right, so while Abdul may be preparing to come through, there's this other participant with the number 87335770 0195. I don't know your name, but are you able to unmute and tell us something? How is it going for you?
I'm actually Yapsra from MyCook.
Oh, okay, that's great. That's great. All right. Alrighty. Yaps, you may continue, but let me say you are doing a great job at this point. Amazing delivery, and yeah, I think everything is going on well. But before you continue, maybe let me talk a bit about WADA. Remember, we need to remind ourselves of the partners or stakeholders involved with this. Earlier on, MeTTa talked extensively about Beyond the Code.ai and SNet, who is the headline sponsor for this project. So let me quickly share with us a few things about WADA, and then once I'm done, yes, you can take over. So as some of you may have been introduced to WADA already because we have been in the system for quite a while now. WADA is an international organization that has been working since 2020 to drive innovation, education, and infrastructure development across Africa. We operate through a network of local hubs, and right now we are in about 8 countries with more than 10 hubs. And this is where we connect local talent and global opportunities. Our mission is built on three main pillars: education, infrastructure, and innovation. Let me run by you what happens exactly in these main pillars. In education, we run training programs in blockchain, AI, and other emerging technologies, and this help developers, students, and entrepreneurs gain the skills to thrive in this digital economy. In infrastructure, we are building and strengthening tech hubs with stable internet, electricity, and resources people need to learn, create, and collaborate. And innovation, we support startups and developers to design solutions that address local challenges, whether it's in finance, whether it's in governance, whether it's in agriculture, or even beyond. But over the past 4 years, let me say we have completed over 50 projects, hosted hackathons and workshops that have reached thousands, and grown a strong network of partners that include universities, local businesses, and global tech leaders. I want to talk a bit about our partnership with SNET, and because that is being part of the story. We are about combining the SNET AI expertise and platform with our deep community networks so African developers can access and use cutting-edge technologies to build impactful solutions. We have also teamed up with BeyondTheCode.ai, thanks to MeTTa, Saskia, and the team, to keep inclusivity and community-led innovation. And this is at the heart of what we do. So together, these collaborations, I want to say, have made programs like this, the MeTTa language training and hackathons possible. And it's giving you the chance to join and learn new skills. But to put them, I want to really say it's not just giving you the chance to learn new skills, but it's also giving you the opportunity to put them into practice and create something meaningful for your communities in the wider world. So this is just a little I want to share with WADA about WADA. But as we go on, I will be talking more about these entities that is working so hard to bring you this particular program. I want to pause here at this point and invite Yavs again to continue with the beautiful presentation. Yavs, take over. Thanks.
Okay, so the next part that I want to cover is going to be control flows in MeTTa. So control flow in any other programming language, you have different control flows. But the first one I want to cover in MeTTa, you have two ways to control the flow of your program execution, which one of it is if, the other one is a switch. But I'm going to be covering only the if in this training. So you can take a look at the documentation for a complete list of all the functions, all the built-in functions, and also we've already also made some other tutorials on how to set up MeTTa, and you can also check them out. They'll be attached in the resources section. All right, so control flow. Control flow in MeTTa is an if, and if you remember, as I told you before, everything in MeTTa is a function. So even if is also a function in MeTTa. So let me elaborate what I mean. So when you try to control the programming logic flow using the if, you're going to be calling a function called if. You're going to pass the condition in the first as a first argument. You're going to pass the then case as a second argument, and you're going to pass the else case as a third argument. So you're going to follow this structure when you try to execute a control flow or a control logic. So let's write some logic and see it here. For example, if a number is even, then you can say, well, if this number is even, then I want to say the number is even. And you can say if it's not even, then you can say the number is odd. So as you can see, this matches perfectly what we've discussed up here. The first one is going to be the condition, the condition to decide between these two logics. So this is the then case. If the condition is true, we're going to be running this case. If the condition is false, we're going to be running this case. So when you run this function, well, as I told you, it's a function. If you want the function to execute, you have to put this exclamation mark before opening the bracket. So if we run this, it's going to say the number is even. Let me just comment this out to make the output more cleaner. Yeah, so the number is even. So you can use if like so, and if I say, for example, 5, this will return false, so it will become the number is odd. So you can sort of control your program logic using this sort of information, using this sort of function. So let's try to build something slightly more useful than this using the if condition. So remember our previous get name function, we can write a function similar to that, but instead of returning a name, it will just return to us whether the attributes that we give it is a certain type of animal, for example. So we can say is dog, for example, and we can give it the first argument like the one above. So we can say animal type here, pretending that we don't know the animal name, the type of the animal. So we give this to the function. So it's the same function definition. I'm using a pattern matching here. I'm expecting a value of triplets. So the first one is going to correspond to the animal type. The second one is going to correspond to the name of the animal. The third one is going to correspond to the age of the animal. And this is all a single argument for the function. So that's it, the function name first, then the argument, and then we go to the function body. So in the function body, what we want to do now is call the if function and use our previously used functions to define a condition. So what's going to be the condition? Remember, the condition should return a Boolean value. So it has to be whether true or false. If that's not the case, this if function won't work. I can show you right here. If, for example, I say 5, yeah, it's going to return this is a bug type. If I say something else, well, I can literally type something else in here. So yeah, it's not going to execute properly because this something else is not a Boolean. So if it's not a Boolean, the function won't execute. It will either throw an error if it's of a different type, if the type is known. But if the type is not known, it won't try to execute the function. It will just return some gibberish code, as you can see here. So you have to be careful that you are going to pass it a function call that are actually going to return a Boolean value when it's done executing. So in order to ensure that, what we want to do is we want to compare the animal type using this equivalent operator. So we compare the animal type with with what we expect it to be, dog. So if the animal type is a dog, then we're going to say, well, return true, or let's say this is a dog. If it is not a dog, then this is not a dog. So let me just try to format this a little bit better so that you can see it more clearly what we're doing. So yeah, the first one, as I mentioned earlier, is a condition. The condition is saying that this animal type has to be a dog. So if it's a dog, it's going to return true. If it's not a dog, it's going to return false. So if it's a dog, then it's going to say this is a dog. If it's not a dog, it's going to say this is not a dog. So it's a very silly function example that I'm using to demonstrate how we can use the if function. So yeah, let's pass this function an argument from one of our previous function calls, which is here. Yeah. Okay, so let's give it the dog and let's say what this function says. So yeah, as we expected, it says this is a dog. So if this is not a dog, then we're going to say, let's just change this to cat, and it's going to say this is not a dog. So we can write a function, a similar function in MeTTa. So well, you can use a similar function definition to write a different logic. This is just an example logic that trying to demonstrate in a very simple way how you can use an if statement in a function. All right, so let's say we are defining another function called isCat as well. All right, give me a moment. Yeah. So let's say is cat. And well, as you remember earlier, we don't really need the if function here. I'm just using it to demonstrate. You can simplify it like so. So if you want to return a Boolean value always, you can just say, if this is animal type is dog, return true. If it's not, return false, which is very simple. You can write the same thing using if. It's going to be a bit redundant, but if you like the explainability or readability more, you can say, well, if this thing is, if the animal type is a dog, then I want you to return true. If it's not a dog, I want you to return false. You can say this, and it's also pretty similar to what I've written before. And we can do similar to the cat as well. So if the animal type is a cat, I want you to return true. Otherwise, I want you to return false. And we can use two of these functions to write another function which can sort of mimic the sounds of animals, or the two animals. Okay, let's just test these functions out. Yeah, they seem to be working. So let's define another function called sound. So this sound function takes an animal type. It takes the name of the animal, the age of the animal. It's not actually necessary, but just to keep the data that we are passing consistent, we're going to use this. So, or we don't even need to pattern much here. We can just say animal, and the functions can do the work for us. And yeah, let's format this a little bit more cleaner, because we want to return the function, we want to write the function's return type, return, which is actually the function body in short. So we're going to say, if this animal is a dog. If the animal is a dog, I want you to bark. So the sound will be bark. But here's the slightly different part. If the animal is not a dog, then we have to make another conditional check. So if you remember earlier, the if condition takes a then and an else case, and those then and else cases don't necessarily need to be always a symbol. They can be an expression, they could be a function call, they can be anything that is a valid meta syntax. So here I'm going to be nesting another if function call. So if I will say, if it's not a dog, then it must be a cat. So I will say, is the animal a cat? And if it's a cat, it will just return the sound of the cat. So I can also format this a little bit cleaner so that you can see it more clearly. And if it's not a dog, then it's not a cat, and we'll say unknown sound. Okay. So as you can see, we have a nested if function call. So the first one is checking if the animal is a dog. If it's a dog, it returns a bark, the bark as a sound. If that's not the case, we can write in the then case of the first if another if conditional. So we say, if it's not a dog, then it must be a cat. Then we will check if this is a cat. If it's a cat, then we will return the sound of a cat. If it's not a cat, we'll say it's an unknown sound. So we can continue nesting ifs like so, and that's when the switch will become more useful, when you have multiple if values that you're going to be nesting. But this also will work just fine. So let's test the function and say, what's the sound of a dog and what's the sound of a cat? So yeah, let me just comment this out so that you can see it more clearly. But it's printing out bark for the dog and cat meow for the cat. So we can also add, let's say, another data called person. It will say it's an unknown sound. So yeah, that's how you use if conditionals in MeTTa. All right, so let me know if you have any questions before I move on into the next portion of the training. Anyone has a question so far? Okay, just feel free to
interrupt me if you have any questions. Okay, so the next part will be a little bit more about recursion. I'm not going to be covering everything about recursion in MeTTa, but you may be interested in knowing how to write recursive logic. So this is where the functional part of MeTTa comes into play, because in other programming languages you have for loops. You can iterate over different data structures or different ranges or based on a condition and so forth. So those programming languages are most of the time imperative, so they don't necessarily need a function for you to be able to write a for loop. But in MeTTa, everything has to be a function, or it has to follow this expression syntax I showed you earlier. So when you want to perform an iterative logic or to repeat a logic over and over, you have to write a recursion. So that's how you'll be able to do it. So writing a recursion, well, as I assume most of you are familiar with, is actually going to be calling a function calling itself. So the most basic example for recursion is going to be factorial. So we can say, well, I want to calculate the factorial of n. So we're following the same function definition structure. We give it the argument for the function name. And then inside the function body, we're going to say if the n is equal to 0. So that's what's going to be our base case because for every recursion, you need to have a base case. So if n equals to 0, then we're going to return 1. That's the base case of our factorial. This format is a little bit better. But if that's not the case, then we're going to be returning n times the factorial of n minus 1. So this is actually a very simple function, just it may look a bit confusing because we're using a prefix notation. So what I'm doing here is I'm just multiplying n with factorial of n minus 1. So instead of using an infix notation in MeTTa, we use a prefix notation. So instead of putting the multiplication here between n and the function call, we put it before them, and then we use n, then we multiply factorial of n minus 1. And n minus 1 is also, instead of becoming n minus 1 as an infix notation, we're going to say minus n and 1, which is syntactically different, but the meaning is the same. We're just saying, this is just the same as saying n minus 1. So we're calling the function again. So the function will stop and start returning 1 when n reaches 0. But if n is not 0, then it's going to continue to recurse by multiplying the values. So let's test this factorial out. So what's the factorial of 5? Should say 120. And yeah, we can play around with different factorials, and it should work just fine. So you can write these kind of recursive logics and try to remember and mix and play with different built-in MeTTa functions. Like you can recursively try to retrieve an information from your atom space. You can recursively match over your atom space. You can query recursively. Basically, it's like writing a for loop for your query. So if you want to retrieve multiple pre-post information, you can do that by just writing a recursive function, especially if you're familiar with recursion and how to write your algorithms or how to break down your algorithms into recursive logic, you're going to be finding this way of defining function pretty easy. But if you're not familiar with recursion, it's a good time to start investing your time into trying to experiment a little bit with writing common recursive functions and also writing some basic iterative logics using recursive logic. So yeah, that's pretty much most of what I want to show you. But before we finish the training, I want to show you a little bit about defining functions and how we can represent some kind of structures in MeTTa again with a more concrete example, and we'll see how we can integrate this whole thing in Python, and it's actually very easy. And I'm going to show you how we're going to do that, and we'll be ending the session after a bit of time for Q&A. Okay, so let's actually create another file called families.meta and start defining some family relationships. So, all right. So, well, imagine this: if you have a family tree, I'm going to do this. If we have a family tree of say 6 people, how are we going to represent them in MeTTa, and how we can write some kind of queries, both as a form of exercises and as a form of writing them and abstracting the queries in functions. We've seen this a little bit earlier, but I wanted to circle back to it because this is going to be part of the most useful part of MeTTa that you're going to use for your hackathons. For your hackathon project. So there's not going to be much difference here, but we're just going to define some person in databases and then try to represent some relationships between them. So, okay, let's start with someone named Mary, who is 64 and she's a female. Actually, I already have some of the data entries already, so it's just paste them over here because I believe most of you are familiar with how we structured this already at this point. Okay, so now we have 6 people in our atom space. We can start creating relationships between them, and we can say we can start with a husband relationship. So we can say John is the husband of Mary. So this is what this stands for. And we can say, as I mentioned earlier, the interpreter doesn't have an undirected relationship. So if you put a John to Mary relationship, if you try to reverse this relationship, the interpreter won't understand what you mean. So either you have to explicitly write that Mary is the wife of John, or you have to write some form of a rule that tries to infer, given that John is the husband of Mary, we're going to return Mary is the wife of John. And I'll show you something similar like that later on. So let's just keep defining more relationships between the people, and let's say between Adam and Lisa. So Adam is the husband of Lisa. Then parent-child relationship. Smith is the child of John. And Smith also is a child of Mary because they're both his parents. And Lisa is the child of Mary, and Lisa is the child of John. So you can sort of see that these people, Smith and Lisa, are actually siblings, but the interpreter doesn't know that. So that's where writing some kind of inference rule comes into play. So let's keep defining some other people into our database, saying Lily is the child of Adam, and Lily is the child of Lisa. All right, so once we have this people's information in our database, we can start querying the information that we want. For example, one can say, based on the information presented only in here, you can sort of know that Lisa is the child of John, but the interpreter or your code or your program cannot infer that, say, John is the father of Lisa or Mary is the mother of Lisa. So you need to write a query that's going to enable you to retrieve the mother of Lisa, for example. So if, for example, you want to match from your atom space and retrieve the mother of Lisa, you're going to say match from my atom space and write the query child, Lisa, and mother. So you're saying basically who is the mother of Lisa, and you can say, well, I also want to retrieve the information of the mother, or you can basically just say mother. Actually, let's just name this to mother's name, so that's not confusing. So mother's name and then Lisa. So you can have this kind of queries, and it's going to retrieve mother, Mary, Lisa. So as you can see, the results are 2. That's because Mary is also Lisa is the child of both Mary and John. So you need a way to infer that the mother is actually, her gender is female. So if you can't infer that, the interpreter won't be able to differentiate between both male and female. So it's going to return 2 results for you. So it's actually returning Mary is the mother of Lisa, which is the correct answer, but it's also saying that Joan is the mother of Lisa. So to prevent that, we need to make another query into our atom space saying that, well, I want you to retrieve only a person that's named mother name. I don't care about the age, but that person's gender has to be a female. And now you can say, well, I want you to return that person's name and Lisa. So you're saying, well, now I'm sure that if the person is a female and if the person is a parent of Lisa, or Lisa is the child of that person, then I'm pretty sure that this person is going to be the mother of Lisa. So let's run it and see the result. And as we expect, it's going to be only mother Mary Lisa, and the John answer is actually filtered out. So I am hopefully that was clear, but we can also write another query, which is a little bit more compact form of the query above using this composite query, which is actually a simpler way of writing nested queries. So you put you open with a bracket, you put the first comma. Actually, I don't think it matters putting a space between the comma, but then after having the comma here, you will write your first query, which is Lisa is the child of mother name. But before returning, I also want you to check that the person named mother name is who have an age that I don't care about and must be a female. And you can say, well, once this pattern match is successfully executed, I want you to return mother name and Lisa. And you can also store this result back into your atom space because that's the new information that your logic or your program is learning on its own. And see, as you can see, the 2 match queries have the same results. And this one will become especially very useful when you have a lot of queries, more than 2 queries or 3 queries and so on. I'll show you an example in just a moment. Okay, so now let's say you want to retrieve the brother of Lisa instead of their parent. So as you can see, the information only provides that Smith and Lisa, they both share parents, but it doesn't really say Smith is the brother of Lisa or Lisa the sister of Smith. So we can actually do that using a match query to infer that there is a brother for Lisa, or we can actually retrieve all Lisa's brothers. So the way we do that is we obviously start with the at self, percent self, which is actually saying atom space refer the current atom space, and we're going to start by saying that, well, I want to retrieve the child, the parent of Lisa. So I can say here a parent. So once we get the parent, what we're going to retrieve is I want to find other people that are actually the parent, actually the children of the parent. So I can say, well, start with another query, and I want you to retrieve another child of this parent. So let's say parent name. So once we found this parent name, remember, we don't want every children of the parents. We want only the male children. So we're going to write a third match saying that I want you to make sure that this person Y, this child Y, whose age I don't care about, is actually a male. And after that, you can say brother Y Lisa, which is actually saying Y is the brother of Lisa. So let's quickly format this in a way that's easily understandable. So if you remember, match takes 3 arguments. The first one is the space. The second one is the query. The third one, which is this whole part here, is the return type or the return body of the match. So in the return body, we called another match, which takes the same format. It takes a space, it takes a query, takes another match, and then this match also takes another space, it takes another query, then finally it's going to be returning the last result, the body that we want to return. So yeah, we have two match queries nested in the first match here. So let's run it and see what it gives us. Cool. So here we have two results. So I'm going to be explaining why that's happening in just a moment. So let me just clean that up. So as you can see, we have two duplicate results, brother Smith Lisa, brother Smith Lisa. Why that's happening is when we try to match the parent's name, we're actually retrieving two of the parents. One of the parents is John, the other parent is Mary. So for both parents, we're actually running another match query for both of them. So it's sort of like trying to run something like a loop for both of the parents. So both of the parents have a child named Smith because they share this child. So that's the reason this result is duplicated, because of the two parents. So if you don't want this to happen, you can add another constraint saying that, well, since both of the parents already have the same child, I just want to restrict it to a single parent. And you can say, well, this parent, you can modify this match query. Let me just copy it down over here. And you can say, well, I want you to match from self for the parent, and I only want you to consider the male parent, for example, or the female parent, doesn't really matter. So let's say the female parent, just consider only one of the parents. That's all what we wanted to do. And once that match query is successful, we're going to retrieve another query both to the self, that goes to the self and says, well, I want you to retrieve the name Y, which is actually the sibling of Lisa, and you're going to say, I don't care about its age, I don't care about this age, but I want the name, I want the gender to be male. And once this last match query is successful, we can say, I want to return brother Y of Lisa. Okay, so let's format it in a way that's more prettier. And yeah, as you can see, now we have another match query here, which is actually constraining the parent to only one of them, only either the male or the female parent. It doesn't matter which. We just wanted to avoid this duplicate value here. But if we run this query, the query won't actually work, and I'll get to that in a minute, because as you can see, the result is empty. So you may ask, why is that the case? Well, in here, when we try to define a nested match, as I mentioned earlier, these variables you define in the queries are going to be shared with the rest of the match query. So if you can see here, the parent name, if the parent name here is, for example, John, it's going to be replaced here with John when the interpreter is actually trying to run. So the variable is going to be consistent throughout the queries. But here, if you can see, we have another query, but one for the parent, one for the child with the same age. So as you can see, the parent who is John or who is Mary has an age of 64, but Smith has an age of 20. So there will be a conflict there. So if we didn't intend for the variables to be the same, to have the same values, we need to change the name of the variable so that the interpreter won't get confused when it gets a conflicting value. So if we change this as using a different variable, because there are different queries, as you can see, and we didn't actually meant for the age to be the same, we just didn't care about the age. So we have to rename the variable so that they won't conflict with each other. So now when we try to run it, it works. And also, as you can see, the duplicate value has already been omitted out. So yeah, we can write this kind of query to retrieve the brother of Lisa. All right, so as you can see, the match query tends to get pretty bloated as you try to add more and more constraints. This is where the composed query or that comma comes into play. So when you write a composition query, it will become very simpler to read and to write your query. So I'm going to be rewriting the above match statement here using that composite query. So I'm going to say, well, I want you to retrieve the parent of Lisa, and I have another query for this child, another child of this parent name. So I'm retrieving another parent. And I also want you to retrieve the parents, actually to make sure the parent is only a female. I want to make sure that's the case because I want to avoid the duplicate. And finally, I want you to make sure that the person Y is actually a male, so that we are actually retrieving a brother. So the query will change like so. So let's try to format it. So we have 4 constraints here. So once all these 4 constraints are fulfilled, the match is going to return to us only the entry that matches all these 4 constraints. So finally, we can say, well, a person that satisfies all these constraints is actually the brother of Lisa, and this is going to return the same value as the above. So you can write a composition query, which is actually a lot more cleaner than a very deep nested match query. So you can also do that. Just wanted to point that out. All right. So once we are able to write this kind of inference rule, as you can see, this is not actually only a simple query. We can treat this as an inference rule. So we're actually inferring who the brother of Lisa is, who the mother of Lisa is, even without explicitly defining that information in our space. So we can define a function. Let's say get mother of anyone, someone's name, of a child. And then we can put that match query that we wrote to retrieve the mother of Lisa in here as a function's body. So the function, has the name here, it has the parameters, and we are going to enter the function name in here. All right, so let's clean this up a little. Yeah. Okay, so now we give the function a child's name. We take that child's name and put it in here because we don't want to be retrieving always about Lisa now. We are abstracting the logic into a function get mother. So we're going to say child's name. So retrieve the name of the child, and I want her mother's name. And finally, the result is going to be not Lisa, but it's going to be child's name. And this child's name is coming from the function parameter. So you have to make sure that you're using this function parameter carefully, because you don't want to introduce a different parameter in here that's going to be causing the same problem as I mentioned earlier. So if you're not sure whether you're using this, whether you want to use this parameter or not, you can just write a different name. But here I am certain that I'm going to be returning the mother's name and the child's name, which is going to be similar to the function's argument. And we can also do something similar for the get brother of a child name. And we can put this match query we wrote earlier in here. All right. So yeah, we want to change Lisa with child name because we want this to be generic. So we change the Lisa with a child name, and then we're good to go. So now, instead of just trying to retrieve the child, Lisa's brother and Lisa's mother, we have an abstract rule that's able to get the mother of anyone we put in here. So for example, if I say get the mother of Smith, it's going to be retrieving mother Mary Smith. Let me comment this out so that would be cleaner. And if I say mother of Lisa, it's going to say Mary Lisa. And if I say Lily, I think we have someone named Lily. Yep. So if I say Lily, it's going to return, well, Lisa is the mother of Lily. And you can sort of change these rules and create more abstract rules. For example, you can say grandmother, you can create father, you can create brothers, sisters, you can create different rules. And let's test this one out with a get brother for Lisa. Lisa had a brother named Smith, but if we change this to Lily, then it's going to be empty because Lily doesn't have any brothers. All right, so yeah, so that's basically it, how you can define a parameter, how you can define a hierarchical relationship in MeTTa and use much to write different queries and use them as an inference rule to guide your logic and to guide your program down the road. So, any questions so far about the representation and querying, anything in general, before I move on to the last portion, which is actually going to be about the using MeTTa from Python? All right. Well, feel free to interrupt, or you can also keep engaging in our other communities. I'm pretty sure they're going to be sharing the links for you, so you can also ask more concrete examples there. And I'll share you these repos, and you can also try experimenting or playing around with this knowledge graph and creating more of your rules, different rules, like retrieving the mother, retrieving the sister, or retrieving the grandfather, the grandmother, those kind of rules. So yeah, it's pretty easy to experiment and play around with. All right, so let's go to the other part of the training, which is going to be using MeTTa from Python. All right, so as you remember in the previous, in the slides, I showed you how to install instead of MeTTa. The only thing you need to be able to do is install a package named Hyperon. Once you're able to install that, you'll be able to call the command, the MeTTa command from your terminal and run anything you want. And that MeTTa object is also accessible through within your Python code. So you can import it from the package Hyperon. You can import a class named MeTTa. All right. Okay, so once you import this class named MeTTa, you can create your own MeTTa object. And then you can interact with this MeTTa object like you would interact from the terminal. So one thing we can try doing is that, let me comment this one out. You can actually try loading your MeTTa files into Python and then run them from the Python object. So this opens for you a possibility of integrating the MeTTa into other programs. For example, if you write your backend logic using Flask, if you plan to integrate these rules or these inferring mechanisms into an LLM, for example, you can use this Python as your interface and connect it with different wide range of applications. So here, what I'm going to do is I'm going to open my file, family.meta file, and I'm going to load everything in here into my MeTTa object. So this is like bringing everything I've written in this file into the MeTTa object so that it's accessible in there. Then after that, I can say run, for example, the functions that I've been running there. I can run the functions in here. I can just do anything I want like I would do from a MeTTa file. The only difference is I have to wrap it in a string. So I can say, well, I want you to run this and want you to retrieve the mother of Lily. And I'm going to store that on a variable. And I can print its output. Okay, then let's run this, and we have this information here. So As you can see, it's wrapped in a list already by default. So this is how the MeTTa object is going to, the Python object is going to be returning the outputs from running MeTTa from Python. So we can say always give me the first output. So this will be exactly how the MeTTa is going to be returning our values. Then we can do different sort of things. We can even do match operations here. I can say, just like we've been doing within MeTTa, I can say match from self person Lisa whose age and gender I want you to retrieve. And I want you to put the age and gender in here and return it. And make sure you have this exclamation mark. It's easy to forget. If you don't have it, it's not going to return any result. It's just going to put this expression into your atom space and keep quiet. So if I try to run this now, it's not going to do anything because it doesn't have any results. It's going to return empty and it's throwing an error. So I have to make sure that I have this exclamation mark so that the result will be correct. It's saying her age is 27 and her gender is female. So you can do different things. For example, you can ask the name from the console and say enter your name, and then you can use that to replace this with the name, and the query will just work fine. Now it asks for the name. I'll say Lisa, then it retrieves. I can run it again. I would ask for the name. I'll say, well, Smith is going to return it, what the result is. Well, you get the idea. You can write this kind of queries using MeTTa. And you can also call the functions as I showed you earlier. You can also add information into your MeTTa file, into your atom space, basically, which came from your MeTTa file. You can populate it from MeTTa, or you can populate it from Python, depending on the direction of your code. So I can say, for example, I want you to add someone named Bob into my atom space. And remember, if I didn't put this exclamation mark, it's going to put it in my atom space. If I put it like this, if I put an exclamation mark to an expression which doesn't have any function definition, it's just going to return the expression. So I can just quickly demo that here. And you can sort of see it. Let me comment this one out. Yeah, so it's just going to be printing this person, Bob, age 0, male. It's not going to return any, and it's not going to add anything to our atom space. That's not what I want, so I'm going to change that, and I'm basically trying to simulate if Lisa and Adam had a new child. So I'm going to add person Bob. There's some new person named Bob who just got born, and he is a male, and I don't need to store this output because there's no result that's going to be returned. We're just adding something to a space. And we will add another relationship between Bob and Lisa, because Lisa is now the new mother, the mother of Bob. And also I'm going to add Adam here because Adam is also the father. And then if I try to match from my space, who is the mother or the parents of Bob are, I can do so like this. And if we print it, oh yeah. If we print this, we get two of them, which is Lisa and Adam. And if we run the previous function we defined, remember, Lily didn't have a brother previously. So if I run that function, get brother for Lily, now since I have a brother entry for Lily, it's going to say, well, brother Bob is a brother of Lily now. But if we comment this out, it's going to say, well, Lily doesn't have any brother. So you can update your space like so. So yeah, this is basically it. Everything you need to know about MeTTa regarding with your hackathon. So let me just give you guys some moment if you want to ask more questions, or if there's something that you want me to go over again, I'll more than happy to do so. And if that's not the case, I'm already done with my presentation. So just let me give you guys a moment if there is any questions that you would like to ask. Well, if that's not the case, I think I'll give the mic to Wada, and maybe they can guide us from here. I am done with my presentation, and feel free to ask any questions you have either here or in the WhatsApp community that will be shared with recently. I also would like you guys to try out. I'm going to share the repository that I was just presenting right now. I want you to try out the last part of the presentation, especially with the matching for family relationships. So you can try defining your own functions as an exercise before the afternoon session for you guys to set up MeTTa and get a little bit feel about how you can define some rules like get sister or get fathers or grandfathers, something like that. So I encourage you guys to play around with that. And yeah, I'm done with my presentation unless they don't have any other question. We'll see them in the afternoon session. If there is something else that needs to be said, I think Sam, you'll be. I'll give the stage to you.
Yeah, what else to say than to say that you delivered a very excellent presentation. Thank you very much. Yes, this is very great session. I'm very excited about that. And I'm sure our participants can also attest to that. Thank you very much. At this point, and especially as nobody seemed to have any questions or any contributions whatsoever, maybe we can draw this morning session to a close. Thank you to our facilitator from ICOG YAPS, who has done a great job this morning. Thank you, everyone. And at this point, we can bring the curtain down and see you at 2 p.m. EAT or UTC +3. Thank you and see you later. Bye.